Hey everybody, it is good to be back. We are going to start here in about 3 minutes, and we are going to take a look today at our good friend momentum. And we'll take a look at impulse and momentum theorem. We'll do a lot of great stuff. So one of the things I'm going to do is I'm going to open up a poll. This poll is going to ask you a non-physics question, and let's see what you think. So there's some basketball games going on here in Indianapolis, and Final Four coming up on Monday, I guess. So I went ahead and asked a little question. If you know, or if you think you know who's going to win, go ahead and put that in there. And we will kind of make our way from there. So tonight is about momentum. So hopefully you are ready to go here. We'll get you going here in just about 2 minutes. We've got one vote already. And we'll take a look here. Once everybody gets in, we've got 2 votes, both for the same team. I like it. I like it a lot. If you don't mind, there is a Pear Deck. Log in there. So if you can get connected to Pear Deck, it will make it so that you can answer some questions that'll keep you involved and active. And they're not difficult questions, but they will help you think about momentum, impulse, and the impulse momentum theorem for the AP Physics 1 test that for some of you is coming up very quickly, and for others might not be till the end of May or even the beginning of June, depending on which one of those options your school has decided to offer. I know some of you are doing the first one coming up here at the beginning of May. Some are doing the end of May. A lot of people are doing the end of May. So if you're doing that, that's great. That one's still pencil and paper. There is a poll there. If you don't mind answering the poll question, we'll see what you think. As you come on, go ahead and hop on to Pear Deck, and we'll get you started here. It looks like it is time to get going. If you have not checked out the poll, here is the poll. So who's going to win the NCAA Men's Basketball National Championship? So I'm going to give you about 10 seconds to vote. If you want to vote, it's either Baylor, Houston, UCLA, or Gonzaga. Totally up to you. Whoever you think will win. And we'll give you just a little bit more time here to vote if you want to vote on that. And if you don't want to, that's okay too. All right, here we go. Let's go ahead and let's start focusing on momentum. So right now it looks like our voters have chosen UCLA, the underdog. All right, excellent job. That's beautiful. And I will turn on the chat. Here we go. Okay, so I have one question here from Anna. It says, Ms. Warner, did you teach the content not on the AP exam, but is in the CED? No, we will not do anything for electrostatics, electricity, or waves. And I'm not going to have my students do it either this year. I have students that move on to AP Physics C, and they can get that in AP Physics C. So I'm not going to teach anything that is on the CED that's not being covered this year. And that's on purpose because I want to make sure that my students are ready to go. All right, here we go. Let's go ahead and get started. I'm going to start this, and then I'm going to also put in the chat a link to the Pear Deck. So if you want to get on and do the Pear Deck, and you've come in a little bit later, that's absolutely fine. So this one is about Unit 5, which is momentum. And please remember the stream is being recorded. It might appear on our website, YouTube, or other public channels. So if you ask a question, your Zoom name may appear on the screen. So actually, I might just call you by name. So if you want to avoid that, you can do that. really easily by just not putting your real name down. So remember, at ThinkFiveable, go ahead and tweet things out. You can go to Instagram, YouTube, let everybody know that we're doing some reviews and that we're trying to do our best to get everybody ready so we can all strive for a 5. And that's what we want everybody to try to do, at least try to pass the exam. This one's not an easy one, but now that they've taken those last 3 units off, it should be a lot easier than it has been in the past. So we're going to do next week simple harmonic motion at 4 p.m. Eastern time next week on the 10th. And then after that, we'll take a look at torque and rotational motion. That one is at 7 p.m. on the 15th. An awesome free response tips and tricks. So we're going to look at the experimental design. We're going to look at QQT, qualitative quantitative translation. We're going to take a look at paragraph length formation, and then we're going to look at just some short answer questions so that you know how to maximize your effort on each and every single one of those. Tonight's stream is on impulse versus momentum. We'll look at the impulse momentum theorem. We're going to take a look at collisions in the momentum cheat sheet. We're going to take a look, just a little look at conservation of momentum. Then we're going to practice with momentum conservation diagrams. If we have a little time at the end, we will play some GimKit, which is super fun. GIM, G-I-M-K-I-T. All right, here we go. Impulse and momentum. So impulse is really just the force that acts on an object times the change in time. And the units for it are a kilogram times a meter per second. If I want to hit a golf ball really far, I want to use a big force and I want it to make an impact for as long as possible. So swinging very hard sometimes makes that happen. Sometimes if you swing really slowly, that makes it happen too. But that's kind of what we're looking for, is a big impulse would have a big force and typically a big time. Momentum here is the mass times the change in velocity. So what we're looking for is the units, and the units for momentum are also a kilogram times a meter per second. So because impulse and momentum both have the same units, that must mean that they are the same thing, and they are. It's just we use a different equation for each one. But when we say that they're equal to each other, so F net delta T is equal to M delta V, that just means that we're using the impulse momentum theorem. And that helps us explain a lot of things, anywhere from how airbags work to why you want to use a wooden baseball bat and not marshmallows. So we'll talk a lot about that tonight. Here we go. This is where you're active. I'd love for you to tell me which activity would require more impulse. Accelerating a soccer ball from rest to 10 meters per second, accelerating a medicine ball from rest to 10 meters per second, or the same for both. And then when you explain, what I would love for you to do is put down 1 or 2 words that explain why. So 1 or 2 words. You don't have to be very wordy. You can use very few words to explain this, but just give me a couple of words that might tell me why your answer is correct. I'm seeing some great answers so far. I like it. Very nice job. Love it. Cool. Very good job. And hopefully I answered your question. I know some teachers are going to teach electrostatics, electricity, and waves anyway, and that's absolutely fine. I think you can always learn a little bit from those, and that might help you on the exam in terms of just doing free response questions and thinking about how they're structured. So just writing in general, sometimes that helps. All right, so I'm seeing a lot of good answers here. I'm going to give you just a couple more seconds. But some beautiful answers. Remember, if I show anybody's answers, your name will not be on there. And that's on purpose. We make sure to keep everybody anonymous so that you feel free to go ahead and answer. Remember, you learn more when you make a mistake than you do when you don't make any mistakes. All right, let's check out some of these answers. So love this one. Accelerating a medicine ball from rest to 10 meters per second. So there is more mass there, and that's exactly the two words that we're looking for. So the change in velocity here is the same. It is a 10 meter per second change in velocity. So the only thing that's really different here is the mass. So again, heavier, more force is needed. So I love that. That's a great way to explain it. Ball mass is larger. Good. That one doesn't have an explanation, but that's okay. Whichever one has more mass. And they even included the equation for momentum. So excellent job. Greater force has to be applied, and it is because we have a bigger mass. So excellent job. Very, very, very nice. Now, if you've logged into this Pear Deck, the best thing that's going to happen is I also included all of the answers that I like to give. And so you will see your answers as well as the answers that are quote unquote correct, or at least one of the correct answers. And that will come to you via email. We'll also put a link to all of the takeaways is what they call them. All right, let's check this one and see if this one makes sense. So which activity would require more impulse? If I slow a car from 60 miles per hour to 40 miles per hour, if I slow the same car from 40 miles per hour to 10 miles per hour, is it the same impulse for both? And then whichever one you pick, go ahead and explain. Yes, the greater the mass, the greater the impulse. Because remember, impulse is both force times time, and it is mass times change in velocity. So if your change in velocity is the same, then it depends on which one has a bigger mass. If they have the same mass and the same change in velocity, they would be the same. All right, again, I'm seeing some excellent answers here. Very good. Excellent job so far. So remember, it's both force times time and mass times change in velocity. Both of those give us impulse. So seeing some excellent answers. So for this one, oh, good question. So is the time the same for both cars? I will say that the time might be different. It might be the same. I think that one we just have to be really careful with. For this one, we're thinking more about mass times change in velocity, and then that will dictate the force times change in time values. All right, excellent job. I'm going to post some of these. Let's look and see how we did. So I love this. It is correct to say that it is slowing the same car, same mass, from 40 miles per hour to 10 miles per hour. This one does have a 30 mile per hour change. This one only has a 20 mile per hour change. So even though this one has a much greater speed at the beginning, this one has a bigger change in speed. So the impulse required to slow this car would be much bigger because the velocity change is bigger. So here we go again. Same thing here. I love it. Excellent job. Good job again. So looks like everybody's getting this, and this is fantastic. I love what you've done here, kind of showing everything that you can. So if you have time on the AP Physics 1 exam and you can go through and do this, that would be excellent to do. I love this. While both cars have the same amount of mass, when you slow from 40 to 10, the change of velocity is greater than 60 to 40. So excellent, excellent, excellent. I love, friends, love this. Beautiful job going through and explaining these. Excellent job. So here we go. I just said bigger change in velocity for the second car. And some of you have much better answers than I do. So good job. Wonderful. Now this one makes it a little bit more difficult. So which activity would require more impulse? Is it landing a jump while flexing your legs, bending at the knees, landing a jump while keeping your legs straight or locking your knees, or is it the same for both? So this one's a little bit more difficult. It's not as bad, but it is a little bit more difficult. So on this one, and I just put this in the chat, the time is a factor for this one. And as a hint, you can think about the mass of this person and the person's change in velocity. I think that's the important part of this one. So which one of these would require more impulse? Landing a jump and you bend your knees, landing a jump, and you keep your legs straight. That would be bad, by the way. You would not want to do that. So don't try it. Love it. You guys are thinking. I love the different answers we have for this one this time. Excellent. So remember, if you don't get one right, that's okay, because we are going to help you with an explanation here for this one. Maybe another 10 seconds or so. All right, let's take a look and see what everybody said. So the first person says, bending the knees takes more force and essentially more time to reach the ground. So they said landing a jump while flexing the legs. This person said landing a jump while keeping your legs straight. The velocity goes to zero almost instantly in the second scenario. Okay, that's cool. This means that the change in V is higher, so the impulse is needed. All right, so that's what they said. This person said the same for both. It's the same person. The mass is the same. And this is the cool part. They said the change in velocity is equal. So think about it. If both people jump down and at the top, they don't have any velocity, as they fall, when they hit the ground, they will have the same velocity. So that velocity will be, let's just call it 10 meters per second. When they hit the ground, they both will go from 10 meters per second to 0 meters per second. So the mass and the change in velocity when they collide, so we don't worry about the free fall, we think about at the point they hit the ground at 10 meters per second until they come to a stop at 0 meters per second. That means the mass and the change of velocity are the same. And remember, we said that impulse is mass times change in velocity. So the difference here is the force for one of these people is huge because the time of impact is super small. And that would be for the person on the right. The person on the left, the force is very small for them because the change in time, the impact time, is huge, just really big. So this one is actually the correct answer. It is the same for both. So same mass, same velocity, but your FT are different. And I think that's the big thing. So if you said landing a jump while flexing the legs, then you were incorrect. However, we will go through and we'll do a few more things to help you understand this a little bit better. So lots of people did try to say it would require more impulse to land a jump while flexing your legs. And the actual answer is it is the same for both because you do have the same mass and you're going to go from like 10 meters per second to 0 meters per second when you hit the ground. But when you bend your knees, it takes a lot more time, so the force is much smaller. And here the time is very small, so the force is much bigger. So let's take a look at what that actually looks like. Here is Newton's second law of motion. Now, most of the time, we think that it's A is equal to F over M. And for this one, we usually think F equals ma. But Newton actually wrote this law as F is equal to the change of momentum or the impulse divided by the change in time. So what I'd like for you to do is rewrite this expression, solve it for delta P, and somebody has already done that, and it is 100% correct. Very nice. And let's solve this for delta P. So what would that be equal to? Good job. Excellent so far. Seeing some great answers here. So this is how Newton actually first wrote the second law of motion. He said the change of momentum divided by the change in time is equal to the force on which acts on an object. So I love it. Excellent job so far. Seeing a lot of great answers here. Good. Beautiful. So here's the reason why we do this. When you look at the answers that everybody gave, we know now that according to our new equation, I can have impulse as either delta P, m delta V, or F delta T. All of those represent impulse or the change in momentum. So it's really easy to confuse the definitions of these because they're all the same. So we can have delta P, we can have F delta T, or we can have M delta V. All of those are the same thing. So you'll see lots of people have put the same thing, which is awesome. I love it. So here's my answer. I just put delta P in here. You could also put M delta V or F delta T. They all mean the same thing, but we look at them in a different way. So let's go back. If I jump, which method of landing a jump involves a greater impulse? So let's see if you remember the answer to this one. Was it flexing your legs, locking your legs, or was it the same for both? So which method of landing a jump involves a greater impulse or a greater change in momentum? So we're looking at, is it flexing, is it locking, or is it the same for both? So remember, for this one, we're really thinking about M delta V. That makes this one easier. You could think about F delta T, but you're going to need to be really careful to think about how those relate. Yeah, here we go. Okay. This one kind of helps me see who is really starting to understand it and who might need a little bit more help, which is fine. So this one, you'll notice, is the same for both. We said it has the same mass and the same change in velocity. So beautiful, beautiful explanation. This one, same thing, same for both, same for both. So I think you're starting to get it. Now let me help you with this just a little bit more, because I think in the next slide, here we go, same for both. In this next slide, we're going to think about using F and we're going to think about using T. So I'm going to actually switch over and I'm going to use a program called Canny, and I'm going to do just a new blank page. And I've got my two people. So I've got my person here, and I'm going to have to use my mouse. Oops, they've got their legs bent. Sorry about that. And they land, and they are super happy. And then we have, and I'll make this bigger so that we can see it. And then we have our person that lands and is not happy because they break their legs. Because when they come down like this and they hit the ground, you'll see that that is not good, okay? So let's think about this in terms of M and v. I'm going to type, ooh, that's really huge. So let's change this. I'm going to change this to 12. So this one is m, and then I'm going to put in a delta here. So let's find delta. So there's m delta v. And I am going to make this one a little bit bigger. So let's go ahead and make this whole thing a little bit bigger. So we're going to go maybe 18. So there we go. M delta V. So that M delta V for this person and the M delta V, whoops, and the M delta V for this next person is going to be exactly the same. So let's go ahead and put that in. So they're the same size. But if I think about force and time, the force on this first person is going to be small. But the change in time for this next person is going to be gigantic. So we're going to put a gigantic T in there. If we think about this person on the right, the person that locked their legs, we have a gigantic F, but they have a very small change in time. And so you'll notice that this person, when they jump and they bend their knees, even though the impulse is the same as the person on the right, the person on the left has a small force because the impact time is so big. And the person on the right has a huge force on their knees, and the impact time is super small. So if you want a lot of force from something, we try to make that impact time small. And if you have the same momentum change or the same impulse, if I want the force to be small, I make the time really big. So using what we just did, I'd like for you to just draw for me over here on the left side. Let's think about the person who flexed their legs and the person who actually went through and they kept their legs straight. Show me what happens with F and T. So show me what happens with F and T. And we just did it. I just want you to repeat it. So let me show you one more time. We've got M delta V is the same for both. For the person who bends their legs, they have a long impact time and a very small force. The person on the right, who's not smiling, has a big impact force because there is a very small time. So here, go ahead, and what I would love for you to do is show me here using big F and little t, or little f and big T, what's happening. So show me with a big F, little t, or a little f, big T, what's happening to each person. So on the left, let's do the bending legs. And on the right, let's do the straight legs. And some people are writing it out, and that's awesome. So our impulse or our change in momentum is exactly the same, but the way that the force and the time act is different. Excellent job. I'm seeing some really good answers here. I think you're starting to get it. I'm just trying to think about how the force and the time work together. Ooh, very nice. So I'm going to show you another answer in somebody else's handwriting. And here is a really great answer. I love this one. So force is small, impact time is huge. Here the force is huge, but the impact time is very small. So excellent job. Love it. Let's go ahead and take a look at this next slide. This will kind of show you what I wrote out for this one. So if this was on the AP exam, these are the types of questions that they're going to ask. They don't typically ask you a lot of questions about having to solve for different things. Instead, they want you to explain the physics. So don't expect to use your calculator very much on the free response part, especially. Instead, remember that you need to answer questions, and you want to do these in some of the best ways you can. So in a couple of weeks, we're going to do a lot of how we answer questions effectively, how we do it very, very quickly, but we get right to the point and we answer thoroughly enough, we can get our points. All right, so let's do the same thing. Let's think about this for a car. Dashboards, when they first built cars, were made either out of metal or out of wood. And they've changed that now. The manufacturers make the dashboards padded. So if you get in a car and you're on the passenger side, there's usually an airbag in there too. But if the airbag doesn't come out, they've made sure that those dashboards are somewhat padded so that if you hit them, that you won't get hurt. What I'd like for you to do is I want you to draw an arrow from each one of these three statements to either the small f delta t side or the big F small delta t side. So draw an arrow. So when it says which of the two above explains why dashboards are padded, it's either small f big delta t or it's big F small delta t. And you can either type those letters in if you want to try to do that. You can write them in, or you can just draw an arrow from the statement up to which equation you want. So we'll give you just a little bit of time to do that. I want to see if this makes more sense now. The second statement says, which of the two above explains why airbags are useful? And the last one says, which of the two above explain why baseball bats are made out of wood and not out of something soft like a marshmallow? So I've seen a lot of really good answers. Excellent. Ah, very nice. Good job. Seen some really good answers here. Excellent. Very good. So remember, for this one, you either want the small f, big delta t, or the big F, small delta t. So if we think about dashboards in a car, if something is soft, does that mean that when you hit it, you are going to have a long time of collision or a short time of collision? They used to have dashboards that were made out of metal or just wood. And so they would have really short collision times. Now they're padded. So that collision time is much bigger now, which makes a big, big, big difference. All right, I think looks like got some beautiful answers here. All right, I'm going to show one answer. Let's take a look at this answer. So this person did a great job on the first one. Which of the two above explains why dashboards and cars are padded? And it is because we want a really small force. We want our body to hit that and slow down over a long period of time. Airbags are useful because they also follow F big delta T. So small f, big delta T, because we want a long period of time. When the airbag comes out, I know it looks like it's really quick because it is, but then when you hit the airbag, you slowly decelerate. The very last one, perfect job. So this one is big F, small delta T. So let me show you the answers that I've got here. I'm going to move this away so that you can see the bottom a little bit better. So for the first two, they both obey the small f, big delta T. We want that time of collision to be really big. For the last one, we want the time of collision to be small so that there is a huge amount of force on the ball. Excellent job. Let's go ahead and move to collisions and momentum. So this is a cheat sheet. Now, of course, you can't take this with you on the AP exam, but I think if you go through and really start to reason these out, they'll make a lot more sense. There are 4 different types of collisions. There are three things that happen that are different in terms of whether something is a stick, a bounce, or an explosion. If I see two things and they explode, they come apart from each other. The collision type is called an explosion. And if we measure the kinetic energy before and look at the kinetic energy after, the kinetic energy after is much bigger. So if you think about maybe a firecracker, when that firecracker goes off, pieces of that firecracker go in all directions. And if we add up the kinetic energy, it is much greater after the explosion than it is before. There are two of the different types that both are a bounce. A lot of times teachers make the mistake of saying that a bounce is only elastic, and that when two things bounce off of each other, it is not inelastic. And that's not true. So for this one, we have to be really careful, because for something that is elastic, where you have two things that bounce off of each other, if they bounce off and the total amount of kinetic energy is the same before as it is after the collision, that one is elastic. If two things bounce and there's a sound made, or there's heat lost, or something is deformed or bent, then the kinetic energy before is much bigger than the kinetic energy after. So if you've ever seen a car collision and two cars bounce off each other, they make a pretty loud sound when they do that. And when they come off of each other, they typically go apart slowly versus very quickly when they make that first contact. If two cars are driving down the road and one rear ends the other and they stick together, that is what we call a perfectly inelastic collision. So when they stick and they're perfectly inelastic, the same holds true as it does with inelastic. We lose some kinetic energy. So these are different types of collisions, either explosion, elastic, where the kinetic energy is the same, and then we have inelastic and perfectly inelastic. And the only way to tell the difference is one of them bounces and the other one is a stick. So let's practice these a little bit. We want to know what kind of collision it is. So I'm going to open up PhET. This is a really cool way of looking at the different collisions. I've got two spheres. One of them is number one. The other one is number two. Number one has a bigger speed than number two, and they are going to collide. And when they collide, they're going to bounce. So we're going to try to figure out, is this elastic or is this one inelastic? So remember, when they bounce, if it's elastic, we have the same kinetic energy before as we do after. So let's check and see what happens. Oh, one more thing that I needed to tell you. Even though kinetic energy might not be conserved, for these collisions, all of them, because we're going to say there's no outside forces acting on them, all of these conserve momentum. So here, notice that it does say conservation of momentum equation. So we are going to conserve momentum in all of them, but not kinetic energy. So let's take a look at this first one. Notice that we have 44 or 0.44 joules of energy in the beginning. So we're going to make them collide. And then in the end, they do bounce off of each other, but we have a kinetic energy of still 0.44. So in the chat, what I would love for you to do is tell me, is this a elastic or inelastic collision? So no energy was lost. The two just bounced off of each other. Is this one elastic or inelastic? So we did not lose any energy. You could put either E or I in the chat and let me know what you think. Is this one elastic or inelastic? Notice that our kinetic energy did not change. So in the chat, just let me know, is this one elastic or inelastic? Good job, Pratush. Excellent. Good, Anna. So this one, as you can see from everybody, is elastic. And it's elastic because our initial and final kinetic energy are the same. Let's do another one. I'm going to reset this. I'm going to change some things around a little bit. Reset that, reset this. Let's move this over a little bit. And let's see if they bounce or not. So we're going to start with the same amount of kinetic energy, 0.44. They're going to bounce, but this time when they bounce, notice that my kinetic energy decreased. And instead of 0.44, it's now 0.04. So what kind of collision is it that bounces and I have kinetic energy that is lost? We had a bounce and we have kinetic energy that is lost. Is it elastic E or inelastic I? Yeah, very good. It is inelastic because we lost some energy. That's probably one of the toughest ones to think about is when they bounce, you really have to pay attention to energy. You can't tell just by the bounce whether it's elastic or inelastic. So let's go back and let's do one more. And this time we're going to start with a kinetic energy of 0.44, and the two actually stick together now, and we're left with a kinetic energy of 0.02. So is this one elastic, inelastic, or perfectly inelastic? So you can do EI or PI. Good, starting to see some good answers here. So this one is perfectly inelastic because the two stick together. And the only way that this happens is if our initial kinetic energy is bigger than our final kinetic energy. Excellent job. Let's go ahead and move to the next one. So let's take a look at this. This is a good way of representing a collision. So in a railroad yard, we have a train being assembled. There's an empty boxcar. It's coasting at 3 meters per second. It strikes a loaded car that is not moving, and the two cars stick together. From here, we know that the event is a perfectly inelastic collision. Each of the boxcars has a mass of 9,000 kilograms when empty, and the loaded car also has 55,000 kilograms of lumber. And they want us to create a momentum conservation diagram. I'm going to go ahead and go to the next one, the next slide. I'm going to show you what this looks like. Then we'll do some math. Whenever you use a completely momentum conservation diagram, one of the things that we put in is the event. So this one is totally or perfectly inelastic. The initial object is the boxcar. It has a mass of 9,000 kilograms, and we said that it's moving at 3 meters per second. I took 9,000 kilograms and I multiplied it times 3 meters per second. That means it has 27,000 units of momentum. The second car is 64,000 kilograms. That's because it is the 9,000 kilograms when it's empty and 55,000 kilograms when it's loaded with that much. So you add the two together to get the 64,000 kilograms for that loaded boxcar. But remember, it's stationary. So it doesn't have any speed, and therefore there's no momentum associated with that car. In the end, they stick together. So I added the two masses together. 9,000 plus 64,000 gives me 73,000 kilograms. I know due to conservation of momentum that the total amount of momentum should be 27,000 kilogram meter per second. I don't know what the speed of the final two cars is. I do have an equation down on the bottom, and you'll see that equation is just the mass of the 9,000 times the velocity plus 0, because we know that second car is not moving, is equal to the mass of both cars together times the final velocity. What we'll do next is find the speed of the coupled cars. So I'll give you a little bit of time to try this one. You'll want to notice we've already found the momentum of the 9,000 kilogram car when it's moving at 3 meters per second. You just need to find VF, or the final velocity of the two cars together. So I'll give you a little bit of time to do that, and then we'll check some answers. Seeing some great answers already. Don't forget your units. Those are very important. On the AP exam, you would want to show all your work here. You do not need to show work. If you want to just use a calculator and plug everything in, you sure can. Excellent job so far. Seeing two really good answers so far. Other people are working. All right, in the interest of time, since I have a couple of good answers here, I'm going to go ahead and show you what the answer is. So this one is 0.37 meters per second. Now remember, if you had 0.369 or 0.368 and you leave it that way, that's fine. On the AP Physics exam, we don't worry about significant digits. I always tell my students, go ahead and make sure you always have two non-zero digits, or if you can use two digits past the decimal place, go ahead and do that. If it's a really big or a very, very small number, use scientific notation, but only leave two numbers in your answer. If you put too many values too many times, they don't like that. They'll count off points. So this one is 0.37 meters per second. Excellent job. Here's the next one. So I'm going to actually have you do this one. I have an astronaut of mass 80 kilograms, carries an empty oxygen tank of mass 10 kilograms. By pushing the tank away at a speed of 2 meters per second, the astronaut goes in the opposite direction. I will let you know that the original velocity of both the astronaut and the oxygen tank together is 0 meters per second. So there's no speed for the two initially. After the collision, let's say that the speed of the tank is 2 and the velocity then is negative 2 meters per second, since it's going in the opposite direction as the astronaut is. So we'll make that 2 negative. The event here obviously is an explosion. So we haven't done an explosion yet. So this is a good one to do. You'll want to put in the event explosion, and then the initial object mass. We know we've got two things. We have 80 and we have a 10. And when you multiply those times the velocity, that's 0. Then on the other side, we have 80 and 10 again, but we have a negative 2 meters per second for that oxygen tank. And we're not sure what the speed of the astronaut is. So I'll have you fill in the chart the best that you can. Looks like a lot of you are already working on it, which is awesome. So very, very good. This is a good way to go through and think about momentum collisions on a free response question. So if you need to sketch something like this or kind of remember what we did, that will help you keep track of everything as you go through, because we know that we want to, whenever we conserve momentum, we need to have the same amount of momentum before the collision as we do after. So a lot like energy, where when we do energy, we always say if we conserve energy, we need to have the same amount before and after. All right, excellent job. Got some good work here. This one is an explosion because two things are together and then they come apart. It doesn't need to be loud and big. It can be a very small explosion. So if I take a basketball and I shoot a basketball, then that is an explosion. It doesn't have to be like a firework or dynamite. It can just be something simple. If I kick a soccer ball, that might be a bounce unless I am holding the soccer ball. If I throw the soccer ball from the sideline, then that would be an explosion. So explosion doesn't always have to mean that it's loud and produces fire. Smiley face. All right, so I'm seeing a lot of good answers for this. Let's show you kind of what this looks like. Notice that there's no net momentum when we begin. That means that when we're done in this explosion, there should not be any net momentum. We do know that the 10 kilogram oxygen tank is moving at -2. So we have, and this didn't come out real well, but we have -20 kilogram times meter per second momentum for that oxygen tank. That means that the astronaut needs to have +20. And we do see that is correct on this side. Because of that, those two, when you add them together, they end up equaling 0, which is what we had at the beginning. So the next question that I have then, and I'll give you time to do this one, is what is the speed of the astronaut? So how fast is the astronaut moving in the end? How fast is the astronaut moving in the end? Remember, the left side of this equation is equal to 0. So that'll make it a lot easier to find the actual speed of the astronaut as that astronaut moves into space. Seeing some really good answers so far. Very good. Nice job. Beautiful. So remember, to get to the number answer, we really have to understand each one of the different types of collisions. We need to be able to show work, and sometimes they might just have you do it in a graph or a chart like this. Sometimes they might have you use an equation, and you'll always come up with the same answer, of course. But a majority of the work is where you get your points. Excellent job. So I'm seeing a lot of good answers here. Nice. Beautiful job. A lot of correct answers, which is good. So let's take a look. Here is all the work. So somebody put 0.25 meters per second. That is correct. There's another one that I selected. This one's also correct. So another one, 0.25 meters per second. Here's the correct answer with the correct work, and this is 0.25 meters per second. You have to make one of the two negative. It really doesn't matter which one is negative. If we made the oxygen tank positive velocity, that would be fine. We would still then end up with a negative 0.25 for the astronaut. So if this one's positive, if the oxygen tank is positive, we know the astronaut is going to have to be negative since it says that the astronaut recoils in the opposite direction. Excellent job. Let's take a look at this next one. This one's a little different. We have a 2-kilogram melon. It's balanced on a circus performer's head. There's an archer that shoots a 50-gram arrow at the melon with a speed of 30, and the arrow passes through the watermelon and emerges with a speed of 18 meters per second. The one thing that they don't tell you is the melon does fall off of the person's head, but it doesn't do it very quickly. So what we'll do is, this is what kind of collision. So go ahead and just fill in the event on this one, and then I'll show you what the charts should look like. So where it says event, tell me what you think it is. Is this a explosion? Is it elastic collision? Is it inelastic collision? Or is it perfectly inelastic? So just tell me the event, which is the type of collision. So remember, I'll put all the different collision types in the chat. So we have explosion, we have elastic, we have inelastic, we have perfectly inelastic. So pick one of those 4 to put in next to the word event, and let's see what you choose. Remember, the first thing you want to do is think about, is this an explosion? Do 2 things that are together come apart? Is it a bounce where 2 things are apart that come together momentarily and then they separate again? And then the last type is perfectly inelastic, where 2 things come together and stay together. Yeah, it could be, Annika, it could be positive. If it asks for speed, we could say that that would be positive, and that would be absolutely fine. If it asks for velocity, then we would definitely need to make sure we have a sign in front of it. All right, perfect. So good job. So I am seeing the correct answer is inelastic. It is a bounce. So even though we went through it, we're going to consider that a bounce because they are apart, they connect, and then they're apart again. So that is definitely a bounce, which is inelastic. We also know kinetic energy is lost because the arrow slows down. Even though the melon speeds up, it's not going to speed up enough. For the next slide, you'll see how I filled it out. You'll notice that the momentum that we have is only 1.5. So 1.5 kilograms times a meter per second. And that's because that 5-gram arrow is really only 0.05 kilograms. Be very careful. You always use kilograms, meters, and seconds. The very last thing that you'll want to do here, and I'm going to show you this since we're running out of time, is to find the speed of the melon. And notice that even though the arrow goes from 30 to 18, the melon only picks up 0.3 meters per second of speed. And that's because that melon has a lot more mass. Notice that it is 2 kilograms and the arrow is only 0.05 kilograms. So it does pick up a ton of speed. I want to leave a little bit of time for questions here at the end, but I also want to remind you that Brianna is going to go over to Discord, and you can ask more questions in Discord if you want to ask them in that format. I'm going to stay here for just a few more minutes, and I will answer any questions you have about what we did tonight. If I was to say there's one thing that is super important, I would say it is that chart that has all of those collision types. So this one, when you get this, and we'll put the link here in the chat in just a second. This is probably the most important thing that you're going to need. Besides thinking about how force and time go together in terms of whether something is has a big force, little time, or a small force and a big time. So I think that's the biggest, those are the biggest two takeaways from today, are this cheat sheet that is really helpful. And then always thinking about M delta V and F and T and how F and T can be big and small. So I'm going to end this and put in here Fiveable for 4/3/2021, and we're going to call this momentum. And I'm going to save it, and it's going to give me a link. And I'm going to put this link in the chat. If you click on the link, remember, it will take you to a message that will say, hold on just a little while, because it's going to take a little while for the all the data to process. But once it does, it will bring up a Google Doc for you. So right now you might see this, and it will calculate a little bit. But once that is over, that's it. All right, if you have any questions, you can ask them in the chat, and we'll answer whatever questions you have. And then in a minute or two, if you want to hop on over to Discord, I'll put that back up, and you can go to Discord, and you can ask more questions or hop in and just kind of chat with people. So that one is at fiveable.me/fiveable-forums. So if you have any questions, let me know. If not, have an awesome weekend. If you're on spring break, make sure you get some rest. Keep thinking, but definitely let your body and your mind relax for a little while. And I think other than that, we will see you next time. Remember, I think our next one is on simple harmonic motion. So thank you all for coming. I really appreciate each and every single one of you. And hopefully I will see you on the 10th. That is next Saturday. And we will definitely do simple harmonic motion. All right, everybody. Thank you so much. The link to the document for Pear Deck is in the chat. So you should see it right above. Let's see. Let me know, Anna, if you see it. It should be, it's the one that says https://app.peardeck.com. Awesome. All right, everybody. Thanks so much. We will see you next week.